So I want to start today's seminar. So we are really glad to have Cynthia continuing with the exposition of log-concave polynomials and applications.
Great. Yeah. Thanks for coming in person or remotely. Please, ask lots of questions. I don't have a strict agenda, so please ask lots of questions if you have them. I'm mainly going to assume a lot of the notation and content from last time, but feel free to ask for refreshers on things. I will give a refresher on some of the definitions. So I'm concerned with polynomials with non-negative real coefficients that are homogeneous of degree d. So all of the monomials have total degree d. And we call this Log-concave. On the positive orthant, if either it's identically 0 or as a function on the positive orthant, log of f is concave. Concave, i.e. that its Hessian is negative semi-definite. Hessian is f times the Hessian of f minus the gradient times its transpose, all divided by f squared. But this is negative semi-definite at every point, whenever I plug in any point in the positive orthant. And then we were interested in a slightly stronger condition. We say that f is completely log-concave. CLC. If whenever I take any directional derivatives in the positive orthant, this resulting polynomial is log-concave. Where, just as a reminder, this directional derivative is just the directional derivative with respect to w. And so last time we gave a characterization of polynomials that satisfied this and said that they have a very tight correspondence with combinatorial things called matroids. Oh. This is, forgot to check the board. And so last time we said that for such a polynomial, there's many independent characterizations of being completely log-concave, or which is sometimes called Lorentzian. The one that I gave last time as a nice way of efficiently checking this is that whenever I take d minus 2 derivatives to get down to a quadratic, the quadratic form I get has at most one positive eigenvalue. And that along the way all of the polynomials are indecomposable. And just as a reminder, this meant that I can't write it as the sum of two polynomials in disjoint sets of variables.
That's including f, right?
Including f, yeah. So if I take no derivatives, then I include f, yeah. And then the third one that I wanted to add on to this, because it had appeared sort of previously in the literature, is that f is strongly log-concave. So just to become sick of the word log-concave, where this means that all of the coordinate derivatives are log-concave. Log-concave plus for all alpha.
And here you also needed the f to be indecomposable.
No, that's actually, so last time we said these two were equivalent, and I think it's, so it's not hard to see that this is true, right? That if I'm allowed to take all directional derivatives, then I can take the coordinate ones. But in fact, we saw last time that if you have a log-concave polynomial, then it is indecomposable. And so you don't need any such assumption. If you know that all of the derivatives are log-concave, here we're only using the ones where we take derivatives down to a quadratic. And here if I say, I know all of the coordinate derivatives with respect to coordinate directions are log-concave, that's enough. That will imply that all of these are indecomposable.
Really? But if you just took f of f, two functions which are strongly log-concave, one acting on one set of variables, the other acting on another set of variables, and you take their sum.
The sum might not be.
The sum is not indecomposable.
Yeah, it also might not be log-concave.
But all of the derivatives will be log-concave.
No.
But the derivatives will be exactly the derivatives of the.
But f won't be log-concave.
What?
F won't. The original function won't be log-concave. So this includes, as you say, this includes f.
Ah, okay.
Yeah.
Okay. That's again. Okay.
Yeah. And so then, so last time we said that if so log-concavity implies decomposability because otherwise the Hessian would be a block, two blocks, and there'd have to be at least one positive eigenvalue. Yeah. So not exactly.
I just missed what did you meant on f itself.
Yeah. So here, I'm demanding all derivatives, including the sort of empty derivative, to be log-concave. And so this is, I just wanted to throw this in because it, in some ways, it is the easiest to state. And also it had been, I think, more well studied as a thing.
This is Groovitz definition?
Yeah, I first saw it. So Groovitz, over 10 years ago, had a paper on studying strongly log-concave polynomials and showing that they have, I'll state one of his theorems, but saying this is what you need for sort of his capacity results. And he called them strongly log-concave. I guess I don't know if he came up with this as a terminology.
I think it did, but it doesn't matter.
Yeah. Okay, and then I'll state one more theorem from last time, and then we'll start new stuff. So the other theorem from last time was that if you have a multi-affine polynomial, so where all of the monomials are square-free, corresponding to subsets of 1 through n of subsides, use this for the product of variables corresponding to that subset. If this is log-concave, well, let's say it's completely log-concave. Then the support of F, so the collection of subsets that show up with non-zero coefficient, are the bases of a matroid. And moreover, every matroid shows up this way, where we can take all the coefficients to be 1. Moreover, for any matroid M, if I just take sum over the bases of M, the maximal independent sets, and write down the corresponding square-free monomial, this is and so last time we proved the second statement, and that's the harder of these two.
Can you let's say what's the notation? Is binomial notation?
So I'll use x to the s for the product of variables.
What is the?
Oh, and I'll use n choose d for the collection of subsets of 1 through n of size d. I wanted to briefly talk about the first part of this theorem because I think it sort of touches on these questions of the importance of a Newton polytope that we talked about a little bit last time. If I wanted to prove this first statement, by the theorem last time, we said that you can characterize matroids based on the convex hull of the indicator vectors of a set. So if which is exactly going to be the Newton polytope of this polynomial f. And so what I want is that the Newton polytope, so the convex hull of all of the indicator vectors of the s's that show up with non-zero coefficient, I want that to be a certain type of polytope. And the characterization was in terms of the edges of that polytope. I want them to only come in certain directions. And so we can actually understand those edge directions by taking a degeneration of this polynomial. So imagine we have the Newton polytope of f. So this is the convex hull of all the monomial exponents that show up. And suppose we're interested in its edges. So let's pick out, we're going to pick out one of them with a linear function. So let's take W, so that the inner product with W maximizes an edge. E, the Newton polytope.
You will still look at edges even if it's higher dimensional polytope.
Yeah, even if, because the characterization I want is in terms of the edges.
Yeah, I'm just stressing that the picture is a special case where it's not evident that the edges will not be maximal faces, they will be edges.
Yeah, yeah, they are honest edges. And it's a polytope, right? So I can, if I pick a face, I can find a linear function that picks it out. And then what I can look at is I can look at let's think about what happens. So if I really write f as a sum c alpha x to the alpha, then let's think about what happens when I scale the ith. I pick some parameter lambda, and I scale the ith coordinate by lambda to the w sub I. And xn. Then what does this do to a monomial? Well, if I pull out all of the lambdas, then what I'm going to get is, exactly the inner product of w and this monomial alpha. And the monomials for which this is the biggest, assuming lambda is greater than 1, the monomials for which this is the biggest are exactly the monomials that lie on this edge.
So what is biggest? You say the monomials for which it is biggest?
For which this value is biggest.
The inner product.
The inner product,
Yeah.
yeah. But that's going to be also the power of lambda, right?
Okay. So you pick the largest degree in lambda. The largest degree in lambda would correspond to this edge.
Yeah. And then what I'm going to imagine doing is letting lambda grow. And what's going to happen is these terms, the terms corresponding to this edge, are going to dominate. And in particular, I can rescale. If this is, w times alpha equals, say, the maximum m, then if I divide by lambda to the m, and then take lambda to infinity, then what I get is just the sum over alphas in this edge. So as lambda goes to infinity, these are going to dominate, and the rest are going to go to 0. And I'm just going to get the sum of terms along this edge. These are called the initial, sometimes called the initial terms. And the point is that each of these behaves nicely with respect to log concavity, and complete log concavity. Rescaling the variables, everything I'm doing is with respect to the positive ordinate. So rescaling the variables by some positive numbers is fine. That's something that preserves complete log concavity. Scaling globally the polynomial by positive coefficient is fine. And the thing that takes a little bit, or slightly more thought, is that this set of polynomials is closed. So I can take, so if for every lambda, this polynomial is completely log concave, I can take a limit. And the limit will also be completely log concave. And so what we get from this is that all of the initial forms, all the polynomials corresponding to faces of a Newton polytope, and in particular edges, but I could use any face for this, will also be completely log concave. And in particular for edges,
is this procedure related to tropicalization?
Yes.
So,
For sure, yeah. I don't want to, because that could be another lecture, but this is 100% related to tropicalization. So at this point, I know that the polynomial corresponding to some edge is completely log concave. And what I can also do, I don't want to do that in too much detail, is I can start taking derivatives with respect to variables, because it's completely log concave. And if we think about what taking derivatives with respect to the Newton polytope does, it shifts the Newton polytope. And decrease whatever variable I'm taking the derivative with respect to, I'm sort of shifting it down by 1 and cutting off whatever didn't have that variable, and it just disappears. And so what I can do is I can start, at this point I have this edge, I can start taking derivatives no, too many. To get down to just something with two terms, to a binomial.
So when you say going down, you mean the degree goes down by one.
Yeah.
The dimension also, or the dimension it doesn't.
I mean, so for example, here, if I just imagine taking this, or even this whole polytope, right? If I took a derivative, then I would sort of be shifting it, I'm raising the floor. So it was two-dimensional, it would stay two-dimensional for a while, and then eventually I might just kill the polynomial altogether. I guess the point is that after taking derivatives, we can assume that there's only two terms that show up here. It just looks like ax to the alpha plus bx to the beta. And in fact, if you keep
where alpha and beta are in E up to
yeah,
under the
up to translation,
like the
yeah,
E after derivatives.
yeah, and moreover, you could assume that they don't have any common factors, because if they did, you could take derivatives with respect to those common factors. So where the support of alpha and so the non-zero, the entries with alpha non-zero and the support of beta are disjoint.
But
now they're disjoint, and we said that's not allowed. The only times when it's allowed is when it's a linear polynomial. So in fact, this means that the size of alpha and the size of beta both have to be 1. This has to be a linear. That's the only time when it's allowed. If it's a linear polynomial with positive coefficients. And that's exactly what we want. Is that these were two, up to translation, these were two elements on my edge. And so what this means is that these are coordinate vectors. Some ei, ej, for some I and j. And what's retained is exactly the direction of this edge. So alpha minus beta records the direction of this edge. I only translated sort of up and down. So what this means is this edge is parallel to ei minus ej. And this was exactly the characterization of matroid polytopes. Was that every edge is parallel to ei minus ej for some choice of I and j. And in fact, so I didn't assume.
How do you know that you get actually two and not just one?
Well, because it's an edge, there has to start off with at least two vertices.
Okay.
Right?
Yeah.
And then don't keep taking, only take derivatives down to when you have two left. Don't take any more derivatives.
Okay. So
just stop. Yeah. So you have at least two to begin with, and then you can always reduce.
Yeah.
Yeah.
Okay. And then
yeah.
Why is it minus? Why does it have to be minus?
Well, alpha minus beta is, so it depends on, so I'm taking this vector.
Yeah, good.
Yeah. Yeah. Right. And so in fact, just as a side note, so this did not require it to be multi-affine. I didn't assume that the monomials were square-free. And so more generally, this shows that the Newton, any edge of the Newton polytope has these directions. And so more generally, this class of polytopes you get are called generalized permutahedra or M-convex sets. And so even for non-square-free, even for polynomials that are not multi-affine, you still can say something about the Newton polytope. And if you restrict to things where the monomials are square free, then you get exactly matroids.
Why don't you get a matroid when it's not square free?
Because the monomials won't correspond to subsets. Like if I took x1 squared plus 4x1 x2 plus x2 squared. Like a matroid, if I do it in terms of bases, is by definition a collection of subsets of 1 through n. And so multi-sets, where I have two ones, it just doesn't.
But I guess there is a notion that Edmonds came up with of polymatroids, and I guess they should correspond exactly to these M-convex sets and the non.
Yeah. So the Newton polytopes you get are the general. So it works out very nicely, even if you expand beyond subsets. Yeah. So I think the integer points of a generalized permutahedron are a polymatroid.
So there is some, I guess, high-level point that maybe June who likes to highlight that there are two very different notions of convexity that come together in this. One is this concavity. One is the analytic one with the Hessian, and one is this M convexity, which you didn't really define, but this. The meaning of have it been parallel to the EI minus EJ or the exchange axiom in
even for the bivariate polynomials, right? You saw the log concavity of coefficients of discrete sequence. I think that's the easiest place to see it, is that, there's this somewhat intriguing translation between functional log concavity and log concavity in the discrete sense, and so one can make that precise in the multivariate sense also.
Can you say it explicitly? Actually, in the two-variate case, the two notions. So one is that you have just a bivariate polynomial, quadratic maybe even, and you have the log concavity is clear. It's just it takes the Hessian as positive, negative, definite. And with the coefficients, it's just the statement you wrote, like a very, very, very special case of the, it's basically the negative correlation, I guess, or the.
Yeah, so in fact, the bivariate polynomials, I'll steal this board. Well, hopefully this answers your question, but at least for bivariate polynomials, ck, x to the k, y to the n minus k. This, is completely log concave. If and only if the coefficients are, satisfy these sort of, again, the problem with this is you have to put too many adjectives and just sort of log concave, but there's all sort of the Newton inequalities. And you shouldn't, for all k, and you shouldn't have gaps. But this is, so this is really saying sort of functional log concavity is equivalent to discrete log concavity in the coefficients. And actually using tropicalization, Peter, Brendan, and Junho sort of make this connection very explicit between M convexity and log concavity, functional log concavity.
get something on the coefficient where in all of these things we kind of forget about the coefficients and we have like characterization using the metric?
Depends on if you believe in the power of the Newton polytope. I mean, so the coefficients still matter, right? I didn't say that you could put any non-zero coefficients. There are some constraints. Yeah, and the last thing that I just wanted to note was actually for multi-affine polynomials. Log concavity implies all of the rest. So F is completely log concave if and only if F is log concave. So then we simplify these many equivalent conditions even further. And the idea is, again, using these sort of initial forms, the idea is you can pick off derivatives of F using initial forms. So for example, if we took the limit as lambda goes to infinity of 1 over lambda, and I just scale the first variable. What that's going to do is it's going to pick off all the terms with a 1 in them. What I'm going to get is x1 times the derivative of f with respect to 1. And this product will be completely log concave, will be log concave, and this polynomial doesn't involve x1, and so in fact, one can show that this is a polynomial in x2 through xn. You can sort of check that if you have products of polynomials in disjoint variables being log concave, then they both individually must be log concave. So one can sort of sneakily take derivatives by taking these initial forms.
And the fact that it is log concave comes from because the closure of taking such limits?
Yeah, so if you take f as log concave,
again, this thing of rescaling.
Yeah, then whatever this limit is, all these operations are allowed. Rescaling, and limits. Yeah, and then, so then you can conclude that this is log concave. And so if we stick with multi-affine polynomials, which I'm going to do for basically the rest of the talk, then we're really just talking, then it's really just about log concavity. And from log concavity, you get all of these other really nice things. Okay. So we said last time that if you have a stable polynomial, multi-affine stable polynomial like this, then the coefficients correspond to distributions with a negative dependence. And log concavity is not enough to completely recover this, but you do get a scaled version, almost negative dependence. Which you can, well, okay, so you can recover, for example, by taking a 2x2 minor of the Hessian of the log. Let's say we pick two coordinates and take the corresponding 2x2 minor. So this, if we actually work it out, this will be the determinant of a 2x2 matrix. And in this coordinate we have this polynomial. I should have given this more room. we will do it here. F times di dj f minus di f j f, and then it's symmetric, so the same thing here. We actually expand this out just to see what we get. It factors nicely. And what we get is 2 times the derivative of I with respect to f times the derivative of j with respect to f minus f times the derivative with respect to both. And what's the point? This matrix should be negative semi-definite at every point in the positive orthant. So in particular, if I take a 2 by 2 minor, it should be non-negative. This should be non-negative, in particular at the all ones vector. And so what does that tell me? This says, these are all non-negative. They have polynomials with non-negative coefficients, so these are all positive. And what that tells me is that this polynomial also has to be non-negative when evaluated at the all ones vector. And so doing the calculations we did last time, you can see this translates to 2 times the probability that I is in the set that I pick with this probability, and the probability that J is in S is greater than the probability of both. So if I didn't have this factor of 2 here, this would be the negative dependence we found last time. And so what I get from log-concavity is a slightly weaker version of this.
You showed us that in the spanning trees it's 1, and I think the unknown matrix where it cannot be 1, right? Or it's not known.
There are matroids with positive, that don't have negative dependence. So it's impossible to get this for all matroids. There's a paper called correlation bounds on fields and matroids. By Schroeder and Wang, where they asked, if I take the uniform distribution on the bases of a matroid, how low can this 2, what's the worst case for this 2? And it's, it's somewhere between 1 and 2, because they show that this inequality does not hold for all matroids. Even for, there are some fairly natural examples for which this fails, like truncated graphic matroids. But then the question is, this bound is true for all matroids, and so then, can one do better? So what I want to do for, let's say, the last 15 minutes of this hour is sketch very roughly an idea of using this for sort of deterministic approximate counting. And then in the second hour, I'm going to talk about the behavior of certain Markov chains that one can associate to these distributions. So the point is that if you have, so we're going to restrict to multi-affine polynomials. So we're going to be thinking about to all the subsets of some fixed size of 1 through n. We're going to associate non-negative numbers to each of them, which up to scaling will give us a probability distribution on these subsets. We're very interested in this probability distribution. Before we do that, I just wanted to, not quite done with the theory. Since it came up last time, just wanted to mention that, so things you can do to a polynomial to keep it completely log concave is the one we mentioned last time is sort of a positive change of coordinates. So if I take f of x, or say x1 through xn, and I send it to ay, where matrix A is say n by m matrix with non-negative entries. Then I claim that if you have a completely log-concave polynomial in x1 through xm, then you're going to get a completely log-concave polynomial in y1 through ym. And the reason is if you try and take some directional derivative with respect to y's of this, then what you're doing, this is really going to be taking the directional derivative in the x's with respect to the vector a times b. And so in particular, if you take a positive vector and you multiply by a non-negative matrix, you're going to get a positive vector. So derivative of f, we've evaluated at x. So you can always make some positive change of variables like this. This includes setting variables equal to each other. This includes a lot of things that you might want to do. And then the other thing that you might want to do, there are many, but is take products. So G. So again, if you have prove this for polynomials in separate collections of variables. Let's say f minus yn and g of z1 through zn, CLC. And I show that their product is also, as Leora mentioned last time, it's clear that their product is log concave, because log turns product into sum, and you add two concave functions together, you get something concave. And then the problem is, what if you start taking derivatives, then it's less obvious. So if I took two positive vectors, I might be interested in taking the derivative of this product with respect to this, where I'm taking A is the directional derivative on the y variables and B is the directional derivative on the z variables. And what I would get is a sum of the directional derivative of vector y.
Together with the part one. It will be that using the chain rule and part one and the transformation one.
I don't think it's, so then I can always set these two sets of variables equal to each other.
Okay, yeah.
There might be a simpler, it's not long, which is why I wanted to just do it. But I was going to use the useful lemma from last time. And then there might be better ways. So this is the sort of thing we need to prove is completely log concave. By an induction on the degree, you can assume that each of these individually are, because you're taking the product of two completely log concave polynomials of lower degree. And so what you need to be able to do is add them together. Add these two things together. And so in fact, you can use this useful lemma that I mentioned last time, which is if you take the derivative with respect to 0b of this polynomial is going to equal the derivative with respect to a0 of this polynomial is going to be non-zero. And so by this useful lemma, you can take these two completely log-concave polynomials and add them together, and it'll stay completely log-concave. Last one. G and induction.
Again, so the induction so by the induction we can assume that it works for lower degree?
Yeah, so I can assume that this product is completely log-concave and this product is completely log-concave. And what I want is that their sum is completely log-concave. And we had this lemma last time, which guaranteed gave conditions on when you're allowed to add two completely log-concave polynomials together and get something completely log-concave out. And it is exactly that they had a common derivative.
Oh, I see.
Yeah, and so here, just by, so these two polynomials, you have a common derivative. And this gives you a hyperplane on which certain quadratic form is negative, and so you can, when you take the sum, it's again negative. And you can bootleg back up to complete log-concave.
And how do you start the induction step? So.
Oh, you have to show for linear. I mean, for
linear.
Yeah, let's say this. I didn't want to do out the proof.
No.
Yeah. Okay, so now we have lots of tools at our disposal. And I give a brief sketch of one way that they're used, and then the next hour will be a longer sketch of how they're used. So one reason one might be interested in this is this connection with capacity that I think Avi talked about very early on in the academic year. And so this, in 2008 actually, Leonid Groovitz had shown that if you have a strongly log-concave polynomial, you can say something about its capacity. So in particular, if you have homogeneous polynomial in n variables of degree n with non-negative coefficients, then the completely mixed coefficient can be lower bounded by n factorial over n to the n times the capacity of f, where the capacity of f is defined as the infimum over all points in the positive orthant of f of x divided by the product of all the sorry, if f is strongly log-concave, then you get this nice inequality. And one of the sort of killer applications that he had for this was when f is just a product of linear forms. So for f is a product I equals 1 to n of sum j equals 1 to n ai j xj. Then this middle coefficient, what is this middle coefficient? Well, that says, I take this product, I want to get exactly one of each variable. Think about all the different ways that I can do this. Because I need to take exactly one x from each of these. You can see that this is actually the permanent of the corresponding square matrix. So one can think of this as a hard thing to find. And one might be interested in finding a lower bound for it. And in particular, he showed that if this matrix A, so if the entries of A are non-negative, then this polynomial is strongly log-concave. And moreover, if A is doubly stochastic, so non-negative entries, and then both the row sums and the column sums are 1, then he showed that the capacity of this polynomial is equal to 1. The capacity of this product of linear forms is equal to 1. And so this tells you that the permanent of a doubly stochastic matrix is greater than or equal to n factorial over n to the n. This was van der Waals. And sort of since then,
yeah, maybe you should say this was a much simpler proof of the original than the van der Waals conjecture and actually more general conjectures.
Yeah. And so the proofs, like they're very slick, but they're not. The proofs of these facts, like one can follow them. They're very clean, nice proofs of these things. And so you can. High level is if you have some strongly log-concave distribution, maybe there's hope of approximating things you would want to compute about it.
How do you say that this polynomial is log-concave? Is strongly log-concave?
The product of linear forms?
Yeah.
Well, every of the linear forms is, if it has non-negative coefficients, and then you can multiply them.
But you're also summing.
No, you sum first. So this is just a linear form with non-negative coefficients.
Oh, okay. Okay. Yeah.
And you can check it's log-concave, and if you take a derivative, it vanishes, right?
Yeah.
And then I told you you're allowed to take products.
Yeah, so that's...
He also, this is also stable, which is how he originally did it. Yeah. So I just wanted to write down a more complicated statement than this, but that hopefully it will at least, that won't make a terrible amount of sense, but will hopefully at least give sort of the flavor of the sorts of things one might try and do. So one of the more complicated things that we showed is that if you, I'll write down the complicated statement and not explain it terribly much. So that'll be fun. Then we'll all be ready for a break. So suppose you have a completely log-concave or strongly log-concave. They're the same variable in two sets of variables of degree n. Then we're going to write down something like this, but much worse. And suppose that you take so for every index 1 through n, you apply the linear differential operator, take the derivative with respect to y and add it to the derivative with respect to z. And you apply this for all I equals 1 through n to f. one can show that this is lower bounded by something. Yeah, okay. We'll write it down, and then let's not worry about it too much. Something that looks like capacity. Over y and z in the positive direction. For all p in 0, 1. So the value, whatever it is, of some differential operator applied to f can be lower bounded by a more complicated version of capacity. Where this is some function of a parameter that only depends on the parameter, and this is some complicated ratio. I don't want to worry too much about what this is, but just like here, the idea is that this is something that there's, you can approximate. And these might be numbers of interest. And the reason I wanted to write all of this down is because using these tools of multiplying polynomials together and taking differential operators, if you have some counting problem and you can write it down in such a way, then you have hope. Then you can try and approximate it. So I just wanted to do one application of this, which is if we wanted to count the set of bases common to two matroids, or rather approximate the number of bases common to estimate, really bound the number of bases common to two matroids. This is a matroid intersection problem. So if I take two matroids, say M and N, of the same rank, I want to approximate the subsets of 1 through n of size r that are bases of both. I claim that I can phrase this as such a polynomial. And I think that aspect is worth seeing. Suppose I took the two matroid polynomials, summed over the bases of m, x, ds. In fact, I want to do something slightly more complicated with the other one. Let's go this one way. Is I want to sum over the bases of something called the dual matroid. Which is the same as summing over the bases of the original matroid, but taking the complement. Both of these will be completely log-concave, because they're the generating polynomials for the bases of a matroid. I know that their product will also be completely log-concave, because I'm allowed to take products. So what I can do is I can apply this theorem. And the point that I want to make is that this value counts what I want, counts the number of bases in their intersection. Is what happens if I apply this differential operator to f and y, f star of z. So this differential operator, what does this do? For every subset of 1 through n, I'm going to get a term where I'm taking the derivatives, this is slightly bad notation, but I'm taking the derivatives of y corresponding to this subset S, and the derivatives of z's corresponding to the complementary subset. Every term in this product, I pick one. Right? And I want to do the same thing. If I think about expanding this product, I'm summing over the bases S in EM, and let's say T in EN, Y to the S, Z to the complement of T. So if I think about, these all have the degree n, because there's a r things in here and n minus r things in here. And if I think about what terms survive, the only way, if I think about taking this monomial differential operator and applying it to this monomial, the only way for this to survive is if these terms match exactly. And so what does that mean? In order, so this, S has to match with S, and the complement of S has to match with the complement of T. And if they do, then this, when I apply this, I get the value 1, because they're all square free, and otherwise I get 0. And so this is exactly going to give me the number of bases common to both. And then using, so I don't want to get too much into the details, but so using this sort of this, so we've phrased something we want to count as something of this form. And so then it's not at all clear from this formulation of it, but then one can give a good approximation to this right-hand sign, and then try to approximate, give bounds on this number. I'll state a rough version of this, which is that there's a convex program that computes some bound B so that the number we want, the number of bases common to two matroids, we get is up to a factor of 2 to the order of the rank. We can calculate this value. So we get a somewhat harsh multiplicative approximation to using this. But one of the takeaways is that using several of these operations, for like multiplication, one can try and phrase counting problems in this way. More than just like plugging in all ones, that will count the number of bases, but one can also do more elaborate things. Okay. So that's what I wanted to do in the first part. Can we take a break?
Cynthia, can I make just a couple of comments and questions about this beautiful part? So you gave the context of Groovitz formulation for the permanent, and you said that can be used for approximation, but you didn't explain why. And I guess there are several points there. Well, maybe the first point to say that permanent, for those who don't know, is a hard to compute function. We can only hope to approximate it. There is a very fast probabilistic algorithm that does fantastic approximation, 1 plus epsilon for every epsilon, Jerome Sinclair Vigoda, and so the interest here is in deterministic approximation. And the best algorithm comes from this lower bounds for stochastic matrices that Cynthia explained, and the fact that capacity can be computed by basically a geometric program, which I guess goes into your result as well. This optimization can be convexified. In the case of the permanent, in both cases, if you want approximation, you need an upper bound as well. So permanent of stochastic matrices is very easy, it's at most 1. And so you get this bound between 1 and n factorial over n to the n, which is about 1 over e to the n. So it's also an exponential approximation, and in fact was improved by Groovitz and Mitsky to 2 to the n. So you also have a similar result. I guess there is a similar sort of easy upper bound on the and you need to compare them, and that's where you get the 2 to the rank exponential. Is there a fast probabilistic? Well, it's what you'll talk about later, the result, but that's for basis. I'm just wondering for, maybe we'll discuss it afterwards. So intersection.
So I'll talk about the probabilistic version for counting or sampling the bases of a matroid. For matroid intersection, I mean, off the top of my head, I don't know, but that does not mean that it is not known. Let's put it that way. I should also say that, so my co-authors, Nima Inari and Cheyenne Oveskaran, they had been, so this was all new to me, but they had been using these sorts of techniques for stable polynomials in order to show such bounds when the corresponding distribution came from a stable polynomial. So this was, in Groovitz also, right? These sorts of, now it looks complicated, but it was, I think, progressed over time.
Okay, so we take a 5-minute break. You ready to start?
Yeah, sure.
All right.
Okay, welcome back. So in the last bit, I wanted to talk about a connection with probabilistic sampling and Markov chains. I want to start off connections. So again, I'm going to assume I have a log-concave polynomial. Then I can take the Hessian of this polynomial and be interested in evaluating it at the vector of all ones. So this will be an n by n matrix, symmetric, with non-negative entries. And if you have if you have a matrix with non-negative entries, one could attempt to associate a Markov chain to it. So the first thing one should do is multiply by a diagonal matrix to make all of the row sums be 1. D is some non-negative diagonal matrix arranged so that the row sums of P are all equal to 1. Then this matrix P will be stochastic. And by log concavity of F, so this matrix has at most one positive eigenvalue, and if I multiply by the rows by non-negative numbers, it doesn't change the signature of the matrix. So this will still be true. Is that the second highest eigenvalue of this matrix P is at most 0. Okay. And so if we were to sort of lazify this, if we were to look at 1/2 of the identity matrix plus 1/2 times this matrix P, then the second eigenvalue would be at most 1/2.
Again, what is the log concavity?
Log concavity of F.
Of F implies on P that it's.
Yeah, implies that this matrix has at most one positive eigenvalue, and I claim then also that this matrix has at most one positive eigenvalue. So the second highest eigenvalue has to be negative, or 0. And also, since this is stochastic, all of the eigenvalues have norm at most 1. And so this, if we look at the eigenvalues of this matrix, then they're going to be all non-negative.
It's really a doubly stochastic. It was a symmetric matrix, so it's a doubly stochastic matrix, right?
So this, yeah. So once I scale, it's no longer doubly stochastic.
Or once you scale, it's not, yeah. No, I mean, if symmetric, yeah, you can pre and post multiply by square root of D. It is symmetric. No, maybe I saw it.
The eigenvalues will be the same as that symmetric matrix, but that matrix won't be. Well, okay.
It doesn't matter. You don't need it. But
Yeah. We'll see also that that all of the eigenvalues of this matrix will be non-negative, and so if I want to understand the convergence of the Markov chain that I get using this, on n elements that I get using these transition probabilities, what I want to do is I want to bound this second eigenvalue away from 1. So I'll be concerned with defining, looking at the Markov chain that this matrix gives, and bounding its second highest eigenvalue away from 1.
So if I give you something that gives you a very fast decay.
Yeah. Because the way I run more than one step of this Markov chain is multiplying the matrix, taking powers. So I just wanted to warm up. So possibly some of you have seen I'm sure have seen various versions of this many times, but I just wanted to warm up with the elementary symmetric polynomial. Which is also even easier because the diagonal matrix will be a scalar multiple of the identity. So the Hessian of this is just all 1 on the off-diagonal entry, and then if we scale by 1/3, then all of the row sums will be 1. And okay, if I take, as I declared I wanted to do, if I average this with the identity matrix, then I get 1/2 along the diagonals and 1/6 everywhere else. And what's the point? I claim that this is the transition matrix for the following one. Transition matrix that I would get for the following walk on the numbers 1 through 4. So if I start somewhere. Some element I in 1 through 4. What I'm going to do is I'm going to increase it to a subset of size 2. I'm going to add j not equal to I uniformly at random. So there's 3 other elements. I'll add every one of them with probability 1/3. And then to get back to an element of 1 through 4, I'll take that subset of size 2 and remove one of the 2 elements uniformly at random. Then the probability of going from, say, starting with 1 and ending up at 2 is what? Well, I had to have added 2, which happens with probability 1/3, and then from that subset 1, 2, I had to remove 1. And so I get a 6th probability of starting at 1 and ending up at 2. And then there's 3, if I go through this, there's 3 different ways I could end up back at 1. I could add any other element and then remove it again. And so I'll end up back here with probability.
It's equivalent of just starting with flipping a coin whether you want to stay or move.
Yeah.
And then move, and if you decide to move, then you move uniformly and you choose.
Yeah, but I want to phrase it like this for purpose. Is that the reason that I want to do this maybe more complicated thing is that it shows that this matrix is positive semi-definite. Is that I can really think of this composition as composing sort of 2 steps. I can write this as 1/6 A transpose, where A is a 4x6, 4 choose 1 by 4 choose 2 matrix filled with 0 1s. And it's exactly the adjacency matrix, the matrix that indexes containment. Indexes containment. So if I look at the rows are singletons and the columns are subsets of size 2, it's going to be 1 if I belongs to the subset JK, 0. So I can really think of this as 2 steps of a process where if I emit a singleton, then I add, and if I emit a set with size 2, then I remove 1. So this shows that this matrix, half I plus half P, is positive semi-definite. And also, I could also compose these steps in the opposite order and define a walk on subsets of size 2. So I could, and the corresponding matrix would be A transpose A. This is going to be a 6 by 6 matrix, where the rows and columns are indexed by subsets of size 2. And the transition probabilities that I would get are the transition probabilities I would get doing this in the opposite order. So start at a subset of size 2, remove one element uniformly at random, and then from that singleton add something back uniformly. So if I started at 1, 2, then I'm going to remove 1 or 2 uniformly at random. So this is going to happen with probability 1/2. And then I'll add something in uniformly at random. So for example, if I want to calculate the transition probability from going to subset 1, 2 to 1, 3, I'm going to have 1/2. The probability of going to 1 is 1/2. The probability from 1 to 1, 3 is a third, so this is 1/6. The probability from going 1/2 back to 1/2, back through 1 is 1/6, but I can do it 2 different ways, because I also could have gone to 2 and then that. So here I go. So here, the only one I'm never going to be able to get to is 3 and 4. There's no, because they don't share any elements. And so I could fill in this whole matrix this way.
Also, it becomes a metway. It's like the fact that the disjoints are that 1, 2 is disjoint from 3, 4, and you.
Well, that's what I started with a matroid. So yeah, but so the thing that I want to note about this is that so this matrix is also positive semi-definite, but then it has the exact same. It's going to have the exact same non-zero eigenvalues of AA transpose. That's the other salient feature. So this matrix has the same non-zero eigenvalues. So we're going to have 2, it's only going to have rank 4, right? Non-zero eigenvalues as 1/2 I plus 1/2 P 6. And so in particular, its second eigenvalue is going to be at most 1/2. So this is a sort of a toy example of something we're going to do that's more complicated. But on the high level, we start with some log-concave polynomial. We're going to use its distributions to define a map on subsets, adding and subtracting elements from subsets. The log-concavity is going to give us some bound on the second eigenvalue of the transition matrix. And also, because we're sort of looking at 2 steps of a larger Markov chain, we're going to be able to relate eigenvalues of walks on subsets of size k with walks on subsets of size k plus 1.
Where did you use log-concavity to bound? So just that the second eigenvalue was less than 0. That was the point. Yeah. So it's at most 1/2. That's yeah. So that's why you will be rapidly mixing.
Yeah. So that's that right now that's the only place I've used log-concavity is to bound the second eigenvalue of this.
But at this point, you haven't at this point you haven't said anything about it, right?
I have, yeah. I said that it's at most half.
Oh, yeah.
So the second eigenvalue of this matrix is at most half, because this matrix, so let's do it with that. So this has second eigenvalue at most 0 by log concavity of this polynomial.
Yeah.
So then this one has second eigenvalue at most half. And then because we're sort of, multiplying matrices in opposite orders, this also has that's all we've done so far.
Okay. And lambda 1 equal to 1.
And lambda 1 equal to 1, yeah. And because it's positive semi-definite, all of the eigenvalues are at least 0. So this is also the second largest eigenvalue in norm. Yeah. And that's a broad phenomenon that will be repeated in more complicated circumstances.
But looking at A transpose and A transpose A, was that for some reason? Is that something you're going to use?
Well, that shows that this matrix is positive semi-definite. And so if you're running a Markov chain,
yeah. Like you already saw that there. Now I'm wondering about this. Why did we get to this step, to this matrix?
Because we also talk about Markov chains on subsets that are bigger than the ones you start. The original one was on singletons. This is already on pairs, and you can continue.
And you can infer. So I got that it's positive semi-definite just by writing it this way.
Yeah, that's it.
But I found the second eigenvalue using the smaller one.
Yeah. Oh, no, okay. My question. I've answered it.
Yeah. Yeah. And so what I basically want to say is that a much more complicated version of this works. And a lot of the same features appear. So are we happy with this example?
Yeah.
Okay. So now we can make it more complicated. So I want to connect this to something called weighted simplified complexes. And then eventually high-dimensional expanders. So a simplicial complex denoted by delta is just a collection of subsets of 1 through n that's closed under inclusion. We'll say that it's pure of dimension d minus 1 if all of the maximal subsets under inclusion have the same size d. And the example to have in mind for this are like the independent sets of a matrix. So for example, the collection of acyclic subgraphs of a graph. Can look at its faces of size k. So this is all just notation. And can look at something called the length of a face in a simplicial complex, which is all the subsets in the complement. So the union is in delta. So if we imagine delta simplicial complex of dimension 2 on 1, 2, 3, 4, 5 things. 1, 2, 3, 4, 5 things, and we take the link. Then one way to do this is, let's say, the link with respect to 1. Then we can look at all of the faces containing 1 and remove 1 from them. So we'll end up with 2, 3. Then what we're also going to do is associate weights. So we're just going to associate positive weights for the top dimensional faces. And faces, smaller faces are going to inherit weights from ones they're contained in. So for every S contained in, no, containing E, S containing E, one size higher. So if I've assigned all the top dimensional faces weights, then the way I'm going to get weights for faces of size of smaller size is I'm going to induct, basically. I'm going to sum up over all of the weights of sets of size that are 1 larger that contain my set. So this is all just notation. And just as a quick note for the polynomial translation, if I have a simplicial complex with such weights, then I'm going to associate to it a generating polynomial, summing over all of the maximal faces, the weight associated to that face, along with the square-free monomial indexing that face. And then, for example, if I look at the link of delta, then what does this do? This is the associated polynomial is, so I'm summing up over all, okay, up to scalar, and sum up over all top dimensional faces, so scalar, that contain S, T, X as a T without S. And this is exactly going to correspond to taking the derivative with respect to those variables of my generating.
So the weights are there just to capture the potential non-uniformity in the bipartite graph relating to adjacent layers, right?
Yeah. So the idea is that I want to write down a random walk on subsets of a certain size whose stationary distribution matches these weights, is proportional to the weights I get this way. And in particular, then the top dimensional weights, if I do this on the top dimension, then yeah, this will allow me to sample from this, approximately sample from this distribution by running this Markov chain for long enough.
So what is the distribution now? Distribution is.
Yeah. So let me tell you the random one. So I'm gonna do a random walk, just like before, between subsets of, say, some size k and size k minus 1. And what I'm going to do is, so if I start at some subset of size k, I'm going to remove an element uniformly at random. This will be probability 1 over k. All my k elements, I pick one, I drop it. And then I'm going to add an element back in. But I'm going to do so with probability proportional to the weight of this. So I look at all of my potential, all the subsets that contain this of size 1 more. They all have some weights, and I choose it proportionally to these weights.
So dropping down is uniform, going up is according to W.
Yeah. And then I could keep going. And this turns out to be a useful thing to do. So this, so there's sort of a down-up walk on subsets of size k, and there's also an up-down walk on subsets of size k minus 1. And really, it's taking 2 steps in this, in this Markov chain on this much larger bipartite graph. And, so if I'm looking at subsets of size k on n elements, then these start to get quite large. This is a random walk on n choose k things. And so the main theorem, the main connection with log concavity is that if the generating polynomial for this weighted simplicial complex is log concave,
Completely log-concave, no?
and it's multi-affine, so it's the same.
Oh yeah, sure. Okay.
Yeah. Is completely log-concave, strongly log-concave, Lorentzian. Is one of the polynomials we like. Then the transition matrix for the down-up walk on these top dimensional faces has second eigenvalue at most 1 minus 1 over b. So bounded, you want to bound it away from 1. And again, I should have written this up here. As with the toy example, this transition matrix is going to be positive semi-definite, so all its eigenvalues will be greater than or equal to 0. And so if you want to look at how fast this Markov chain approaches the stationary distribution, the important thing will be to give a second bound on to upper bound the second eigenvalue away from 1. So for matroids,
if you take our previous example was our previous example, we were looking at the simplicial complex, which is just a tetrahedron going on its vertices, and then we switched to going on its edges, like this. So, and we had lambda 2. We showed that lambda 2 was smaller or equal than 2, than half.
Half, yeah.
Right, and that's corresponding to d equal to 2, because we were on edges.
Yeah, yeah, exactly.
Cool.
Yeah. And then, so so maybe I'll write down the consequence and then say a little bit about why. But so in particular, for matroids, if you start with the bases of a matroid, we know that this is log-concave. This corresponds to the uniform distribution on the bases of a matroid. On one through n, rank D, say, then what this gives is that the total variation mixing time. So starting from any state, getting within to say epsilon of the stationary distribution in one norm, can bound this on the order. So this bound gives us d squared, log n perhaps. And so if you wanted, if you wanted to sample the bases from an arbitrary matroid, you can imagine just running this smart control chain for long enough, and after the right amount of time, it'll be within epsilon of the stationary distribution, which is uniform. Since then, so this has been improved since then. For example, by and then also sort of us again, and then the current state of the art. So with using some other methods, gets this down to like O of D log D over epsilon. But the stuff that I just want to mention today is sort of
So on the off chance you are not going to say it, Cynthia, I'll say this result, the top result before the improvements. This was an open problem for maybe 30 years of approximating the number of bases for almost uniformly sampling from them. And the algorithm was known. I mean, everybody knew that you can move elements in a base and some random function. Nobody could analyze it before all this development.
Yeah, and then to me, one of the miracles of this project was that and also one of the keys to analyzing this was work on local spectral expanders that was developed around the same time, and that matches up incredibly well with this sort of theory of log-concave polynomials, seemingly developed for exactly log-concave polynomials without any of the people developing it having such examples in mind. Yeah, so so the sort of key ingredient of this was work on something called local spectral expanders, which I will attempt to define. So they define so we take a weighted simplicial complex, exactly as I've set up, and say this is a lambda local spectral expander. If the second eigenvalue of some matrix is at most lambda for all face, so to every face we're going to associate a matrix where P sub s is going to the ijth entry is going to be the weight of S union I union J over the weight of S union I for ij not in S. And this is going to define a walk on the link of S in delta. So in particular, this is up to a scaling by a diagonal. This is the Hessian of the derivative with respect to the S variables of F evaluated at the all using this polynomial translation. So developing on a long line of work, including by Eri Mir, who was here, Kaufman and Oppenheim 16 showed that if you have a lambda local spectral expander, then the transition matrix for the down-up walk on this big simplicial complex has second eigenvalue at most 1 minus 1 over d minus d minus 1 over 2. And in particular, if this polynomial, this generating polynomial is log-concave, so we're going to be interested in the lambda equals 0 version of this. The Hessians of derivatives are going to have second eigenvalue less than or equal to 0. And so what that's going to translate into is exactly that the down-up walk on this top face is at most 1 minus 1.
Why is it called local correspondence?
Well, you're localizing here. You're looking at, if you think of this giant simplicial complex, what you're really doing is you're taking walks on the one skeleton, on the edges of links. And so you're sort of shrinking. You're looking at, you're interested in this giant walk on like n choose d things. But you're bounding its eigenvalues in terms of walks on much smaller walks. This, this is at most n choose 2 things.
Can I say, Lior, something to think about to understand it, both the definition and its power. Just think that you are in a graph, and what this tells you, it just look at the neighborhood of every vertex. If every neighborhood is expanding enough, then the whole graph is an expander. That's what it tells you. Yeah. Well, it has a whole history and story that I'm not going to get into. But it's local expansion just around neighborhoods implies, with connectivity, implies that the whole graph is an expander.
Oh, cool.
And yeah, and so zero local. So this weighted simplicial complex is a 0 local spectral expander if and only if the generating polynomial is log-concave. This polynomial and so in particular, your only hope for getting a 0 local spectral expander is to have the have the simplicial complex be the independent set of a matrix, independence complex of a matrix.
Do you have anything about stable polynomials? In the language of these random walks and these omega weights?
Well, if you take a stable polynomial, either it is one.
One implication is clear.
Yeah.
Like, clearly, but the other one.
I mean, you might, one might hope that if you have stability, that it implies something stronger here. Just by logic, right? If you take a stronger condition,
you take a stronger.
I mean, in this language, it's not like you just get a better lambda.
Yeah, that's the best one. But maybe the locality can be improved.
Yes, but I don't want to.
Okay.
so yes, but I don't think it's. Okay. Yeah, and so, well, I just want to. I find this still this whole stuff very. I know there were lectures here last year on this. I still find this sort of miraculous. But the very rough idea is to of the proof of all this is to do a much harder version of what we did in the beginning. Is to so using the same sort of tricks, you can show the non-zero eigenvalues of the down up walk on delta k and the up down walk on delta k minus 1 match. And then also, you can bound the eigenvalues for the two different walks you get on delta k, adding and subtracting. So removing and then adding, or then adding and then removing. Those two both will define random walks on subsets of size k, and you can bound the eigenvalues of their transition matrices in terms of each other. Bound eigenvalues of like the up-down walk. Delta k in terms of the down up walk on delta k. And so this lets you sort of work your way up. So in our first step, we related a walk on vertices to a walk on edges. And what this says is you can relate eigenvalues of two different walks on edges. You take an edge and you add something to it to get a three-face, and then you remove something to get an edge. And from these, using these two, you can sort of bootstrap your way up to looking at the eigenvalues of this potentially giant transition matrix on the top dimensional faces. Yeah. Because I'm already over time.
So maybe you can summarize what you didn't have time to say.
Yeah, I mean, I might have done an example, but I encourage you to work out an example. But just to sum up for the hardcore who are still here, so one, I hope log-concave polynomials are nice. They have nice combinatorics. They let you understand a lot of things about matroids, including inequalities on, for example, numbers of independent sets. You can generate lots of them using operations that preserve log concavity, like taking products, taking derivatives. And then hopefully, what I managed to give you at least an idea of in this talk is that once you have log concavity, it lets you approximately count or approximately sample from the corresponding distributions on subsets, either using capacity in a deterministic way or using this theory of local spectral expansions and running a Markov chain. So there's a lot of it opens up analysis for a lot of interesting tools. Now I'll stop.
Thanks. Yeah, thanks, Cynthia. This was really wonderful. So, all right. Questions to Cynthia?
It's been a long.
Yeah, I have dozens of questions which I'll ask you separately, but I have one general question.
Okay.
So in the in the 80s, early 90s, where all these Markov chain techniques were developed for analyzing or to approximate counting various objects and sampling from them. Yeah, this particular matroid thing got stuck, but one thing that was successful was the approximating the volume of convex polytopes. And yeah, so one can run a Markov chain inside a convex body. There's tons of papers, and I don't know, whoever wants to know can ask me. But one thing that's really nice about the distribution, a uniform distribution on the interior of a convex body, is that it's a log-concave function. And this is used, in fact. And not only is it used, it was generalized to sample not only uniformly from inside convex bodies, but in fact, just sampling from log-concave distributions in R to the n. So works of Impala, Lovas, and lots of others. And I was going to ask you about connections between this kind of sampling and their kind of sampling, if you know.
Yeah, that's very interesting. I don't know. I'm the sampling and the sort of Markov chain analysis side of things is still, I'm like a grad student in Markov chain. I'm still learning all of the
But it didn't come up or was not mentioned in any of your papers, other papers on the sampling process, that other log-concave polynomials just
yeah.
coefficient.
No, that's very interesting. Yeah, I don't know is the short answer. But
Okay.
It would be interesting to look into.
Okay, I'll yeah, we can talk now. Okay, more questions. Yeah. So it's really magical that simultaneously these two theories are developed and match up so perfectly. Yeah, it is remarkable.
Yeah, these were both in 2018, actually.
Yeah, so well, I mean, the idea was developed maybe around, earlier. I think the main the spectral definitions for high-dimensional expanders were developed by Rit Dinur and Tali Kaufman, and in particular, these connections between up-down and down-up, and trying to relate them to the other very different notions of expansion of simplicial complexes, cohomological ones, and these Gromov ones, so on. But anyway, I think they just initiated this and then connected to this local analysis, Garland method, and so on. So yeah, anyway, it's pretty amazing. Okay, more questions, guys. So, okay, we'll release Cynthia to a well-deserved lunch that I still need to buy on campus. Okay, thanks again.